Hello, my name is Joel Randall. This final project presentation will be an overview of the design and implementation of an IoT automated window growing system. Many people like the idea of being able to grow fresh herbs and vegetables in the kitchen, but many have trouble doing so. Not enough or too much water, not enough too much light are some of the most common problems. This project attempts to solve this problem by implementing a 21st century solution that is an internet-connected, automated growing system which reassures the user that the plants are doing well and the system is performing the way it needs to. The smart growing system consists of 5 parts: the controller, planter, sensors and actuators, the algorithms that run on the controller, and also the user interface. Controller selection is important, as the selected controller can have a large impact on how the final project looks and operates. For this system, the requirements were that the controller needed to be adaptable, internet connected, and GPIO. This threw out most microcontroller solutions. For that reason, the single board computer system was selected, because of its full operating system and ability to run as a network server. More specifically, the Raspberry Pi Zero-W was selected for this project because it can run Linux, which has a lot of support, and also it includes an onboard wireless chip, eliminating the need for a Bluetooth or a wireless dongle. The planter itself was constructed out of plywood and is 12 inches by 24 inches by 6 inches. There are holes in the bottom of the planter to allow the soil to drain, and the entire inside of the box is waterproofed. There is also a 2.5 gallon water tank with the same footprint and a fill spout on the front. This water tank was fully waterproofed with Flex Seal so it doesn't leak. I'm now going to talk about the sensors and actuators. The watering subsystem consists of an analog soil moisture sensor, and therefore needing an analog to digital converter. This is a picture of the first soil moisture sensor that I used. It was low quality and very inexpensive. As you can see in the picture, it corroded and stopped working after only 5 weeks. For this reason, a more expensive soil moisture sensor was selected. For the water pump and drip lines, I used a small hobby fountain pump and plastic tubing with pinholes in it for the drip lines. The plastic tubing runs underneath the soil and provides the moisture. For the lighting subsystem, a lux sensor was selected. Lux is the international unit for perceived brightness, and this sensor uses both infrared and visible light sensors in order to calculate a very accurate depiction of this. The growing light was also selected and is essentially optimized for photosynthesis. It does this by providing specifically red and blue light, which are important for photosynthesis in particular. In this way, it can save energy while still providing adequate brightness. Much research suggests that playing music to plants can help them grow. For this reason, a music playing system was also added to the device. The 3-watt 6-ohm speaker bonnet was selected from Adafruit and connects directly to the top of the Raspberry Pi. To this, 2 home theater speakers were attached for high fidelity and good sounding audio. I'm now going to talk about the algorithms that were used in this project. Throughout this project, an agile style development process was used. In this way, each of these segmented functionalities could be planned, built, launched, and tested individually. This is important as it helps to eliminate problems during integration. As each of the functionalities were developed one by one, they were then packaged into Python functions, which could make system integration at the end more smooth. I'm going to do a quick overview of the watering algorithm. It starts by checking the soil moisture from the analog to digital converter using I2C and the SMB Python stack. This value is then converted from the digital value into a float value, which is the literal analog voltage seen at the input pin of the analog to digital converter. This sensor voltage is then compared against a check voltage, which is configured by a soil moisture. If the system needs water, then a 10-second priming pump routine runs first. This 10-second routine steps from 0% duty cycle up to 100% duty cycle, and in this way gives a slow start and allows air bubbles to get pushed out of the system and water to flow better. Once this is completed, the pump runs for a specified duration. I'm now going to talk about the lighting algorithm. It first measures the light. It does this by sampling both channels on the light sensor and then calculates that perceived brightness, or lux. The lux is tracked throughout the day, and the value is stored within a text file. A decision is then made by checking the accumulated light off of the light goal that has been configured. If it's determined that the system needs more light, then one of the plugs is turned on, which is connected to the growing light. The plugs are switched by relays, which are controlled by the Raspberry Pi. The music playing algorithm is fairly simple, and I use the Pygame module for music playback. Music is added to a particular folder on the Raspberry Pi. Any MP3 file that the user wishes to be played to the plants can be put in this folder. The algorithm then randomly selects songs out of the folder and continues to play them until 2 hours have passed. An important aspect of the system is the configuration file. This configuration file allows the system to be used under many different growing situations. The first setting is the soil moisture level, and can be set to high, medium, or low. This is meant to mimic the kind of language you would see on the back of a seed package. There are 2 watering programs. The first watering program gives water more often, but in lower quantities. This is good for keeping a constant soil moisture, which is beneficial for sprouting seeds. The second watering program gives more water less often. This is important for developed plants, as it helps them to grow a better root system. There are also 4 light level selections: full, medium, high, and low. Once again, this is meant to mimic the kind of language you would see on the back of a seed package. Full corresponds to 12 hours of direct sunlight, high to 10 hours, medium to 8, and low to 6 hours. There are also 3 light programs. The first lighting program starts at midnight and runs the light until the daily goal has been reached. The second starts at nightfall and runs until the light goal has been reached. This is good if the planter sits in a bright location and gets direct sunlight during the day. The third lighting program is essentially the first, except that because the growing light can often be disruptive to humans, it turns off from 7 a.m. to 8 a.m. and then again from 5 p.m. to 7 p.m. In this way, it can be less disruptive to humans. I'm now going to talk a bit about the user interface. The first component of the user interface is the settings file. This settings file can either be configured directly through a text editor. This is an example of the settings file. Or a helper script can be run on the Raspberry Pi. This script guides the user through pre-configured setups. The first is a sprouting routine. The sprouting routine is optimized for sprouting seeds and sets each of the 4 settings accordingly. The second option is intended for more mature plants and offers a little more configurability. The third option is a full custom option and gives the user complete control over all 4 settings within the file. There's also 3 log files. These log files are meant to reassure the user that the planter is doing what it needs to be and that the plants are doing well. The first log is a moisture log. At every 30-minute interval, it tracks the soil moisture voltage, as well as including an entry anytime the watering system runs. The next log is the luminance log. Once again, at every 30-minute interval, this records the current measured light level, as well as the accumulated lux throughout the day. The third log is a music log, and this is meant to reassure the user that music is being played to the plants, even if they're not around to hear it. Scheduling of each of the scripts was an important aspect of this project. The Linux cron tab was used to do this. In this way, if the system were to reboot randomly, it could pick back up where it left off once it started back up again. It was discovered early on that script overlap created predictability issues. For this reason, a staggered script schedule was selected. At 0 and 30 minutes of each hour, the soil moisture is first recorded. Secondly, at 01 and 31, the lighting script runs and decides to turn the light on or off. Finally, at 02, every top of the hour, the watering script runs. The watering script is run last as it takes the longest, in upwards of 30 seconds under certain watering conditions. Also at 1 a.m. and 3 a.m., the music script is configured to run. It runs for 2 hours each time. It runs first thing in the morning while we're sleeping because the music I currently have loaded to the Pi is not pleasant for human listening, but rather is optimized for growing plants. This is a picture of the completed system as it sits in the window above my kitchen sink. The watering system has been functioning well and has watered 3 times since becoming fully automated. The lighting system has been performing flawlessly, giving exactly the right amount of light to the plants each day. The music playing system has also been functioning well, although it's too early to comment on the effectiveness of playing music to plants in order to help them grow. Overall, I consider this project a great success, and am very pleased with the way it's turned out. It's been running completely automated, growing plants, for a little over a month, and as you can see, the plants are doing fairly well. Thank you very much for watching my presentation. I hope you have a good day.